See, now in this session, we'll be seeing about when to use the 2D elements for meshing. Okay. So 2D elements are
Okay.
generally used when actually two of the dimensions are very large in comparison to the third dimension, which is what I have explained you, right?
Okay.
So the thing is, I'll just show you first. Okay. So the element shape which is actually used for meshing is one is quad and next one is triangle. Okay, so the additional data from the user, what the software asks for it is the thickness. See, basically you have three dimensions, but the third dimension of thickness is negligible when you actually go and mesh for the 2D components, right? So for meshing the 2D components, you'll be using 2D elements. And there are two forms of 2D elements available for meshing. One is quad and next one is tria. Okay. So the additional data from the user, which the software generally asks, is the thickness. Practical applications where you are seeing is the sheet metal parts, plastic components like instrument panel, etc. So now you can notice down a plate which has been given here, and this is the length portion, and this is the breadth portion, and this is the thickness portion. And the thickness portion is very much negligible when compared to the length and the breadth dimension. Okay, so that is why we regard this as the 2D component. For any 2D component, before even getting onto the meshing part, you should be able to, you should be able to find out the mid surface. Can you see here the orange color?
Yes.
That is called mid surface, which means if you have, let's say, the thickness of, let's say, 10 mm, then you have to exactly extract the mid surface, which is zero thickness. So this is very, very important before doing any meshing, because this 2D, this mid surface extraction will actually help you a lot in actually providing the thickness to the element for proper meshing. Okay, so we'll see that. So this is what been explained now. So quite often we are actually uh, seeing the geometry of thin-walled 3D structures is simplified to a geometric model with a lower dimensionality, which means we are converting the 3D into 2D. So this is actually called as the mid-surface model. The mid-surface model is then meshed using 2D elements. There are two forms of 2D elements, as I said. One is quad and next one is tria. Thus, there is no need for detailed volume mesh. So we don't need to give the 3D mesh, as the thickness of the geometry is virtually assigned to the 2D elements. The thickness will be assigned in such a way that one half of the thickness will be given in the positive direction and another half will be given in the negative direction, which means one half will be provided on the upper side and another half will be provided on the lower side. So these are all certain examples which we are showing where we extract the mid surface. Okay. So I'll show you another clear image where you can see here. Now, just see here, you have the mid surface, right? Can you see here? This is the mid surface.
Yes.
Now, when you provide the thickness, positive half will have half of the thickness and negative half will have the half of the thickness. Okay, if you are not extracting the mid surface, then your meshing might go actually out of the actual thickness. The component might have the
Okay.
thickness of 10 mm, but after meshing, you might see some elements of meshing protruding on the upper side or on the downside. Okay, so this thing can be avoided if you can extract the mid surface properly. So that is the main advantage of 2D meshing. Okay, so in
Okay.
this also you will be able to see here. This is the mid surface. Now, if you say that if the software asks what is the thickness and if you are giving 10 mm, then it will provide half in the positive direction, which is 5 mm, and half in the negative direction, which is 5 mm. Okay. Now, coming to this part, see, 2D elements have two main. There are two main types in meshing of 2D elements. One is tria, and another one is quad. Okay. So this is actually just now, if you take the triangular element, for instance, it has got three nodes. Okay, basically, so there are two types under triangular elements itself. One is called as first order or lower order. The second one is called as the second order or higher order. Okay, or it is sometimes it is called as quadratic. Okay, so out of the triangular elements, if you are using for meshing, let's say for example the previous example of the flat plate itself, if you are going to do the meshing using triangular elements, the meshing will look like this, right? Triangle elements everywhere, triangle elements everywhere, right? It could be a
Okay.
straight triangle or it could be a right angle triangle, anything. Okay, but in general, triangle. So now there are two types in this one: first order, lower order, both are same, where you have only three nodes or the three vertices of the triangle. Whereas if you go higher version of the same element, that is called second order or higher order, or it is otherwise called where in addition to the three corner nodes, you will also consider three mid nodes. So for one element here, it is only three nodes. For one element, it is having six nodes. You remember the first class which I said that for accuracy of your analysis, you should have more number of nodes rather than more number of elements, because nodes are the points where you exactly calculate the output parameters, whereas between the nodes, which is element, you will actually try to interpolate or approximate the result, correct? So which means higher nodes or more number of nodes are preferred. Okay, so this will give you a greater accuracy. Then coming to the one more type of meshing, which is called as quad meshing. See, regarding quad meshing, basically you will have four nodes. Okay, again two classification. One is the first order, or you can call it as lower order, and the second one is called as the second order, or you can call it as higher order, or otherwise quadratic. The same thing. Here on the basic first order, you have four corner nodes alone. But in addition to the four corner nodes, you are also considering four mid nodes. So totally it will have eight nodes here in the higher version. So again, this will give you a greater accuracy when coming to the first order. Okay. Now coming to the point of
Okay.
which element to use. See, generally for any sheet metal or metallic applications of 2D components, you are supposed to use the quad element or quad mesh. Okay, that will actually give you a better mesh. Also, it will give you a greater accuracy for your analysis answers. Okay, whereas
Okay.
if you go for the triangular element for 2D mesh, then it is actually considered as errors, or those are all the elements which you need to rework on it and then remove it, because this triangular elements are actually having a very high stiffness. So because of which your component might show some very much deviation in the answers or the output parameter calculation. Let's say, for example, if you're calculating the stress for a particular component subjected to a loading condition, that will actually provide you an answer which is way far higher or lower than the actual answer. So once when you actually try to mesh using this 2D, that is for metallic. Regarding plastic components, this is most preferred and this is not preferred. Quad is not preferred. So you have to remember. So this triangular meshing is preferred for only plastic, not for, whereas the squad meshing is mostly preferred for metallic and not for plastic. Okay.
Okay.
So the next thing is how not to mesh. So there are few basic things which you have to remember. Anyway, when I'm actually trying to teach you in the ANSA software, you'll be able to see all these things. But before that, I just want to give you an insight that you should not mesh in certain way. So these are all the basic things which you have to remember. Back-to-back triangles should be avoided, and no two triangular elements should be connected to each other directly. Here you can see the quad mesh, but while doing quad mesh, certain triangular meshes also coming, right? Triangular elements are also coming into play, right? But these triangles has to be removed actually if it is a metallic component, right? Now see here, what is the rule? Back-to-back triangle should be definitely avoided, or two triangular elements should not be connected to each other directly. See here, same base, but two triangles are connected back to back, which means that once after meshing, if you are getting this type of mesh, then you have to remove these elements and replace it by quad elements. Okay. Similarly here also, common vertex point, but you have several triangles attached to it, right? Similarly here also, back to back triangle is actually available, right? So these are all the ways by which you should not mesh. Okay. And one more thing I just forgot to tell you, this triangular element of lower version is called as CST popularly in finite element analysis. And you said that you don't have your finite element analysis as a subject or a paper in your UG, right? So this is called as
No.
constant strain triangular element. This is called linear strain triangular element, LST. Okay.
Okay.
Okay. Now, coming here, this is another way, another rule which you should remember. No mesh transition should be there on the constant radius or fillets or curvature. Mesh transition should be carried out only on the planar surfaces. Now, this is the planar surface. This is the planar surface where you can do mesh transition. See, mesh transition in the sense you have got one element, second element, third element. That is all fine. But this is a chamfer area, right?
Mm-hmm.
So these kind of chamfers, fillets, and notches are all considered as critical parameters for design point of view. Okay, because these are all the areas where the stress will be more concentrated. You might have learned about something called a stress concentration.
Yes.
So stress concentration will be
Yes.
generally more on the places where the area change occurs, and that too in the sharp corners, notches, fillets, and curvatures. So there should not be any mesh transition allowed for fillets and curvature area, which means this is good, but this is not acceptable. Where you can see that there is mesh transition, right? This is not acceptable, which means you have to replace it. Okay, so this is another rule. Then avoid triangular elements on the outer edges or holes. You can see here, this is the outermost edge, right? Where you have a triangular element, right? Where you have a triangular element.
Mm-hmm.
Okay. Similarly, around the holes, see, actually, this is the original component which you need to mesh. After meshing, you are getting something like this. This is because the hole is not captured properly. The hole has been now captured as a hexagon, right?
Yeah.
That is because around the hole, you might have some triangular elements present, because of which it is not captured. So our aim is to capture the curvatures properly as per the original component. When you do some fine mesh, this is actually possible. But doing that, you should avoid the triangular elements around the holes. Okay. So the next thing is holes should be modeled carefully with the washer area. Okay. Which means, see, now let us assume that this is our component which is to be meshed. Now let's assume that our hole is say 100 diameter. Now, if you want the hole to be properly captured using your meshing elements, then you should consider imaginary surface around it, which is called as the washer. So now you might ask me a question that what should be the washer's diameter? Roughly, you can take 1.5 to 2 times the original diameter of the hole. If the diameter of the hole is 100 then this washer could be some 150 to 200. Okay. Now, by doing that, you will be able to capture the hole properly. Now, you can see the difference between the previous slide and this slide. In the previous slide, your hole was captured like a hexagon, but in this slide, you can see that the hole is almost captured properly, right? And always try to have minimum 2 layers of elements around the hole, which means this is the actual hole. Imagine that this is your washer area. You have 2 layers of quad elements present.
Mm-hmm.
Okay, so this is how you will
Okay.
do for the hole. And also you remember that holes should be modeled with even number of equally spaced elements. You should not use odd numbers. Like around the hole, there should be always even number of elements like 6, 8, 12, 16. You should not have 5, 7, 9, 11, 13, something like that. Then only you will be able to capture the hole properly and you will get some uniform structured mesh. Okay. And after doing all this meshing work, you will actually have to go and check for the element quality. See, element qualities generally you are checking because whether you are test passing your component after meshing by carrying out these rules, and also you have some uniform structured mesh, something like this. This seems to be a structured mesh, right? So something like that,
Yeah.
this should be passed on, and also from the company's perspective and also from the client's perspective, they might give you what is their requirement. So that requirements should be surpassed by your particular meshed component. Okay, so that is why we go for the element quality check. So these are all the few things which you have to remember. So you have basically for 2D mesh, two types of elements. One is triangular and another one is quad, right? The best triangular element what we actually require from meshing is equilateral triangle. Equilateral triangle, generally, all sides are equal, all the three sides, and the included angle between the sides should be 60-degree, right? This is the most preferred. But if you are getting some right angle triangle or right angle triangle is also fine. But with this kind of triangles are very poor. If you are getting some meshed quantity triangles, then you should actually remove these kind of triangular elements where you get more acute angle or more obtuse angle. These kind of elements should be removed. Similarly, while doing the quad meshing, we actually want all the four faces or four sides should be equal. Something like a square. We don't require a rectangle actually. That is the best mesh what you can actually provide. And the included angles should be 90-degree. But this is also okay, which means if you are getting a triangle, that is also fine. Or if one side of the triangle is alone getting some 60-degree angle, or if you have some distorted square or triangle having a very lesser value of, let's say, 5-degree, that is also okay. But you should not get something like a trapezium or parallelogram. That is not at all acceptable. This is considered as poor mesh. Or distorted square or rectangle having more than 5-degree. That is also not acceptable. So these kind of meshes should be avoided. Okay. Now, these are all the few 2D element quality checks which we generally do for if you go and work in any company, or if you're getting a project from your client, definitely they will give that. Yeah, the client will specify particularly that what should be the warp angle. Okay, so warp angle is considered as the out of plane angle. For your understanding, I have given the definition over here. If you're okay, you can read about this. But the idea of warp angle is they will give you a particular value. You have to maintain within that value. See, ideally, we want the warp angle to be 0-degree. What is the acceptable range? It is less than 10-degree. This I have given. But project to project, from client to client, from company to company, it keeps on differing. He might also tell you that he or she might also tell you to have to maintain the warp angle as less than 8-degree also. That is also possible. But in general, I can say mostly less than 10-degree will be maintained. Okay. And the next thing what we'll see is the aspect ratio. Aspect means it is ratio. Ratio means you'll have a numerator term and you have a denominator term. Okay. So imagine that you have a mesh element like this. Okay. Ideally, this aspect ratio should have the value of 1. What is aspect ratio? Which is maximum element edge length divided by minimum element edge length. Now, if this is considered as the entire element, this is the minimum edge length and this is the maximum edge length, right? Now, if you go for the maximum edge length divided by minimum edge length, the answer should be 1 ideally, for ideal case, for best meshing. But if it is less than 5, is also acceptable. Again, this 5 is a parameter which should be given from your company side or client side. Okay. It keeps on changing from project to project. Then comes the another parameter called quality parameter called Jacobian. Ideally, this value should be equal to 1. Acceptable is minimum greater than 0.6. So this is the one parameter where you are actually seeing the greater than symbol. Okay. So in simple terms, I can say that Jacobian is a scale factor which is arising because of the transformation of the coordinate system. Because you actually try to work on a coordinate system and try to actually transfer that to a global coordinate system. When you try to do that, you will have some changes. So that is why we actually try to measure this Jacobian as a quality parameter check for any meshing. Okay, so then comes the included angle as another parameter for quality check for meshing of 2D elements. So it is actually included or otherwise called as interior angle check, which I have already displayed that for quad elements, ideally we should have the included angle as 90 degree, but acceptable range is somewhat between 45 degree to 135 degree. And also for the triangle, we expect the equilateral triangle. So the included angle should be 60 degree. Acceptable range would be greater than 20 degree and less than 120 degree. So these are all the different quality check parameters which we'll employ for the 2D. Now we'll go and see the 3D. Okay. So when to use 3D elements? So when you will use 3D elements, when all the three dimensions are comparable, none of the dimension is negligible, then that is considered as 3D elements. So here for meshing, you have got four different types. One is tetra, next one is penta, third one is hexa, and fourth one is pyramid. So these are all the four different elements. Under 2D, you have got only two elements for meshing. One is quad and another one is triangular, right? Then the additional data from the user, what the software asks is nothing. Whereas in the 2D case, it asks for the thickness. And one more thing, 2D meshing is called as shell meshing, which I have already specified in the previous video, right? And 3D type meshing is called as solid, or it is otherwise called as volume mesh. Okay. Then the practical applications there we have seen about the sheet metal parts and plastic instrument panels, something like that. Here the practical application is the entire part of the automobile spare parts like gearbox, engine block, crankshaft, everything are actually considered as 3D one. Okay. And you can consider this block also, which is very similar. See, 200, 100, and it is having 50 thickness. So you can't neglect that. Okay. It is not something like 10 mm thickness or 8 mm thickness to consider it for a 2D. Now coming to the version of this, under the 3D element meshing, you have got tetra. Penta is otherwise sometimes called as wedge element. Hexa is often popularly called as brick element mesh. And there is one more thing called pyramid. I'll tell you one thing, that pyramid element is not supported by all computer-aided engineering softwares. ANSYS actually carries this pyramid element option. Okay. So now again you have got the first order and second order classification under each element. First order tetra element will have 4 nodes, whereas second order will carry the mid nodes and include totally 10. So again, this will give you greater accuracy for your analysis answers when compared to this one. Okay, the next one is then you can ask me what is the difference between these two. So it will give you the accuracy, but it takes lot of computational time because each and every parameter has to be calculated at each and every node portions. So here you have 10 nodes for one element. Here you have only 4 nodes. So here the computational time would be less, but accordingly the accuracy will also be less. And penta or wedge element is carrying some 6 nodes generally of the first order case. And if you go for the second order or higher order version, it is carrying 15 nodes of the same element. And hexa or brick is actually carrying 8 elements for the first order case. For the second order or higher order case, it is carrying 20 nodes. And pyramid, I said that it is optional. It is not supported by all softwares. But if there is a software which is supporting pyramid elements, pyramid will be actually more than tetra and less than penta. You can see here, it is carrying 5 nodes of the first order and the higher order of it is carrying 13 nodes. Okay. Now coming to the degrees of freedom for solid elements. See, degree of freedom, generally you might be familiar with that particular term. Okay. Now generally you have 6 degrees of freedom, like 3 translation and 3 rotational, right? A body can move along 3 linear axes, X, Y, and Z. Similarly, a body can have rotation about 3 axes, X, Y, and Z. So totally you have 3 translation and 3 rotational, totally 6 degrees of freedom. Now let's see whether our 3D element supports all the 6 degrees of freedom or not. Okay. So we'll consider this example. Consider a steel scale, okay, which should be considered as 1D, right? Because this length is very large when compared to this dimension and thickness, correct?
Correct.
Paper can be considered as a 2D component and this duster element can be considered as 3D. Now see what they are actually trying to do is they are trying to rotate this. They are trying to, bend this. They were able to do the bending in 1D and in the case of 2D, which is paper, but not in the case of duster, which is because it is having a very high stiffness, right?
Right.
So which means I can say that the 3D elements does not support the rotational degrees of freedom. It has only 3 translation degrees of freedom possible. It does not support rotational degrees of freedom. Okay. Whereas you can easily bend this 1D, which is the scale and the paper. So the next one is, see, also note down one thing that when they try to mesh actually, let's say for example, I'm having a 3D component, something like this. All the 3 dimensions are actually comparable. Okay. Now, instead of directly going for the volume mesh, which is 3D mesh, what the CAE engineer will do is they will try to mesh this surface alone and then try to convert that and drag that element to the entire depth value so that you will get a uniform structured mesh for the entire 3D structure. Which means what I'm trying to say is I'll first try to mesh only the surface, which means it is very simpler for me, which looks like a 2D, right? Then I'll
Yeah.
include dimension and then convert that into a 3D volume detailed mesh. Okay. So mid nodes should lie exactly on the geometry, which means for a parabolic tetra meshing is a basic meshing available in the volume mesh. For a parabolic tetra meshing, many computer-aided engineers prefer to start with linear triangular elements, which means they will try to mesh this surface and then convert into parabolic, which means then they will try to, use this dimension and try to convert that into a volume mesh. So they'll start with a 2D mesh and then try to convert that into a 3D mesh. Okay. So in that process of conversion, the nodes actually might not get projected properly on the curved surfaces or fillet areas. So it should be projected properly and care should be taken. See here, this is recommended because it is actually covering the entire curved structure, but this is not covering that properly. While doing this conversion process, you have to remember this. Then one more thing is when a particular work is actually split among the computer data engineers, let's say that this is my first, this is my second, and this is my third. This is assembled together. So let's say that this has been meshed by a particular group, this has been meshed by another group, and this has been meshed by another group. Now, if they don't have any coordination between them and what they are really doing, then when you assemble, the mesh looks like this. Here, the third group has done some fine mesh, small elements has been used for meshing, right? Whereas the first and second group have done a coarse mesh, little bit bigger element size. Since there is no proper coordination and what is actually being given by the client, if everything is not kept in mind, then while assembling, you will end up with this. This is not at all accepted by any client or company because you should have a uniform mesh throughout the entire body. Even if your body is being split into 3 and separately working upon by the 3 different persons, still you should actually keep in mind of all the target areas and then try to keep the mesh as such. When you try to assemble, you should get a uniform structured mesh. Okay. So the next one is minimum 2 number of elements should be present on the fillets. Now let's say this is my fillet area and fillet area should contain at least 2 elements for better capture of surfaces. See here, I can say that it has been captured using 2 layer of elements. Okay, then only you will actually try to avoid a few mesh elements errors, and your quality check parameters will also be met properly, and your meshing will be done in a good manner. So the next thing is, while doing the hex mesh or brick meshing, again you have to follow minimum of 2 element across the thickness. So even if you consider this thickness, you have 2 layer of elements. So that is actually preferred as good mesh. And then here also you have got some uh, important things. See, use of tetra and pyramid elements while brick meshing. See, brick meshing is something which is called as hex mesh. Okay, and before that you have got penta and tetra, right? Then I said about something called as pyramid elements, right? So some clients will actually allow for few of the tetra elements present during brick meshing. You are doing only hex meshing, but still tetra elements, he will actually allow you to use certain numbers. Let's say for a 2D element, I should actually do the quad mesh alone. But even if I end up with some triangular elements also, that is fine. But I should not go beyond a certain value. So that value would be definitely specified by the customer or the client. Okay. In the same way, while doing the hex mesh for 3D component, you are allowed to use some tetra elements, but it should not go beyond a certain limit. Okay. So you should get the proper instructions from the client side to actually maintain your level of tetra elements, the number of tetra elements present in the component. Okay. So that's what been given here. Then coming to this point, which I was speaking about yesterday. This is actually a 2D case, which you can clearly see. Compared to this dimension and this dimension, the thickness is negligible. And let's say I'm giving the dimensions as 200 into 200, whereas the thickness is only 2 mm. This is definitely a 2D case, right? Now,
Right.
two ways of meshing this. He can directly give a 3D mesh also, or he can directly consider this 3D or convert this 3D into a 2D component and do the 2D. So in both the cases, we'll see the difference. So one person is actually trying to do the 3D meshing for this component. For the same component, another person is considering this as properly as a 2D component and then giving 2D mesh. So this is a quad mesh, what he has given. And the first person is actually trying to give a tetra mesh, which falls under the 3D meshing category, right? Now, if you compare the end result answer, it would be one and the same. Let's say that we are finding out the stress answer. The stress answer is coming around as 1.7 Newton per mm square in both the cases. But the problem is, for a 2D component, if you are using 3D mesh, you are getting the same answer. But see how much number of nodes has been employed? 1496 nodes, which means 1496 points, you will do the stress calculation. And then the number of elements created is 689. Whereas the same component, if you properly treat that as 2D and then do the meshing, you require only 121 nodes and 100 elements to get the same answer. Are you able to get this point? Are you able to get this point?
Yes.
So you should keep that in mind. If the third dimension is negligible, then please do go for the 2D mesh. For all the components, you cannot go and do the 3D mesh. If you do the 3D mesh, you will end up with the same answer, but the calculation computational time will take longer. Which means this person might get the answer in 5 minutes. This person might get the same answer in 30 minutes. Even
So,
though,
so
yeah,
for 2D elements, for 2D, when you model it as a 2D part,
yeah,
the answer is always the same. Either you use a 3D mesh or a 2D mesh.
I have given a simple example. From cases to cases and the complexity, curvatures, radius, fillets, holes, notches, everything is also taken into account. Okay.
Okay.
But what I try to
Okay.
tell through this is unnecessarily, please
Okay.
don't go for a volume mesh for all the components. That's why we actually
Okay.
categorized in the previous video as 1D component, 2D component, and 3D component. Because if you are able to categorize that, 1D means you can just do the 1D meshing itself, right? Where the complexity of meshing
Okay.
is less. If you go for 2D, it is more than 1D. So there is some complexity, but still you can actually do it better rather than going for 3D. 3D, it is more complex. So for
Okay.
a simple structure like this, why are you going for 3D since you are getting the same answer as that of what you have done for the 2D mesh? So
Okay.
that's why that makes the CAE engineer to be thorough professional. Similarly, there is
Okay.
limitation of 1D element and advantages of 3D meshing. See, you know that now this is a stepped shaft, right? So it has a diameter over here and it has some other diameter over here, and you also have some keyway slot. Now, during this area change, definitely you will end up with some fillet, right? So this is the fillet. If you try to consider this entire shaft as 1D and try to mesh, still you will end up with some errors. Why? Because, see, you might have used 1D element to capture this curvatures, which is the fillet, right? But that might not be captured properly. Like few minutes back, we have seen that the hole has been captured as a hexagon, right? In the similar fashion,
Yeah.
this fillet would not be captured properly. So there you can actually try to make use of 3D meshing as an advantage, because along the 3 dimensional, it will try to capture the fillet. So the fillet will be properly captured as per the original component. So the next thing is you also have some quality check parameters. So for tetra meshing, you will check for something called tetra collapse. The ideal value is 1, obviously, but acceptable is 0.1, more than 0.1, or they might also give some value as more than 0.2, something like this. And for your understanding, I have given what is tetra collapse. So this is generally checked for all tetra meshing. Okay. So this covers the entire part of the 2D and 3D meshing. Okay. So the next class,
Sir, I have
yeah, tell me.
one more question. You mentioned about different 3D elements being more stiff compared to 2D elements.
No, under the 2D elements, you have got two category, right? One is quad and another one is triad, right? Another
Okay.
in that triangular element is generally considered as more stiff. See, if you have seen the truss structures, mostly it would be of triangular shapes, right?
Okay.
Because of the nature of its own geometry, triangle is considered as more stiff. Which means, let's say, for
Okay.
example, if I take the same plate problem and imagine that I'm subjecting it to a tensile load, and imagine you are actually trying to capture this entirely using the triangular elements. You are meshing it using triangular elements. Now, this forces won't be transferred properly from this edge to this edge because of the high stiffness value, and you will end up with a lot of errors. Or you might see the variation in answers in the stress value. So this
So we
is
need to choose.
mostly preferred only for plastic components, whereas for metallic components this is not preferred. For
Okay.
metallic
So the
components, quad
element.
mesh is mostly preferred, whereas for plastic this is not preferred.
Okay.
Okay,
So we
so
had to consider the features of the element also when we are. It should match the features of the product. Is it something like that?
yes, yes,
No,
yes,
sorry, the features of the part.
yes,
Some.
yes, yes.
Okay. Okay.
But all these two elements are coming under the 2D category. Keep that in mind. And just a few minutes back, we have been seeing about the tetra, penta, hexa, and those kind of
Yeah.
elements are coming under the 3D part. Okay. So do not
3D.
confuse.
Okay.
Yeah, do not confuse with this. And I have shared with you the same materials. You can go through that once. And I have shared about the GUI interface of the ANSA software, which we'll see in the next video, next session. Okay, so to get
Okay. Okay.
familiarized with the tools, I have actually given you a PDF, which also you can keep as
Okay.
a better handout that will help you a lot and to increase your speed while when using your ANSA software. Okay,
Okay.
so we'll meet in the next session. Thank you.
Okay. Thank you very much, sir. Good night.
Thank you.